Welcome to the QualiMaster Demo video on how to build and adapt Storm pipelines. This video demonstrates the actual state of the project, in particular in building data processing pipelines and preparing them for runtime adaptation. We will first give a short introduction into the project context and then turn to the demonstration video. Stream processing is a promising approach to analyze big data. In stream processing, one or more data sources provide information, so-called data streams, conceptual unlimited sequences of information tuples. These streams are typically characterized using the big three V's: velocity, volume, and variety. Sometimes you find also more V's in some publications. The aim is to derive some form of analysis of the data, if possible analyzed and visualized in real time. A data analysis pipeline defines how data is analyzed and how to obtain the information to be visualized. Several algorithms do exist, such as filtering or sketching. The challenge is to compose them in a user-friendly way so that the resulting pipeline produces meaningful results, if possible, in real time or more technically with low latency. A simple answer for realizing a pipeline is to program it. Programming a stream processing environment requires knowledge in distributed programming and thus is a complex task. In Apache Storm, the framework we are using as a foundation, you have to deal with terms like spouts, which means the actual data sources. Bowls are the units that analyze the data. Some form of linking them, it's called grouping in Storm, here shuffle grouping. Topologies that implement the data processing, we call these overall things pipelines. So-called executors and workers, the physical distributed execution units. And the parallelization, that is the question how you can parallelize your analysis so that it becomes efficient. One core aim of the QualiMaster project is to research how to configure data stream processing in contrast to programming it, and how to enable runtime adaptation to cope with the changing environment, for example, as the three V's may change at runtime. Therefore, the administrator configures first the available hardware for executing pipelines. This includes typical cluster hardware and, in our case, also specialized hardware such as reprogrammable chips or graphic boards. The administrator defines the algorithms that shall be available for data processing. Algorithms can be grouped into families, and this enables dynamic selection of the most suitable algorithms at runtime. Actually, the administrator also defines available data sources and sinks. The pipeline designer uses this information to compose the actual analysis pipelines from data sources, algorithms, and data sinks. The configuration tool, both data pipeline designer and administrator use, validates the overall configuration, in particular whether the composed pipelines are structurally valid and can be executed. If the configuration is valid, we derive program code implementing the pipeline. Actually, we produce code for Apache Storm. Finally, the code is deployed and executed by the QualiMaster infrastructure, which works on top of Apache Storm and specialized hardware. And this entire process is powered by the QualiMaster Configuration tool, which acts as a domain-specific front-end for a generic software product line tool called Easy Producer. Now, let's configure the hardware. Before using the tool, we need to log in to access the model repository. On the left side of the user interface, we see the categories we can configure, ranging from general purpose cluster machines over reconfigurable hardware, data sources and sinks, to algorithm families, individual algorithms, and finally the data processing pipelines. Let's look now into the configuration of a cluster machine. In particular, such a machine has a name, as well as a role in a cluster, here manager or worker. And depending on what you select, this leads to further required settings such as communication ports for the workers. Machines can be added, deleted or cloned to simplify the administration of the cluster. Similar information can be provided for reconfigurable hardware. And the overall entered hardware information is considered as the resource pool and used as a basis for adaptive execution. Let's configure now the data sources and algorithms. Here we look into a financial data source, which is implemented in terms of a Maven artifact and provides data according to a given format specified by the input fields. Currently, sources are configured manually, and we will support obtaining this information from the implementation artifact in the future. The core of the adaptive processing are the algorithm families. Here we look into a preprocessor family, which turns data from a financial source, seen before, into structured data. A family defines its input and output format, as well as parameters that can be changed at runtime. Individual algorithms can be assigned to a family, and these algorithms must comply to the input-output formats and the parameters of the family. Several algorithms are already defined. Here the Hayashi-Yoshida correlation estimator or sentiment analysis algorithms. For example, the preprocessor algorithm we've seen before as the family is implemented using the given Maven artifact and provides compatible in and output fields and parameters. In the future, we will also enable here to obtain this information from the implementation artifact to simplify the configuration. A very interesting part of the configuration is the definition of the data analysis pipelines, because they integrate all the configuration parts we've seen before. In contrast to the previous settings, we do this using a graphical drag-and-drop editor, visualizing the data flow in the pipeline. The pipeline starts at the data sources, here using the financial data source we configured before. There's also the preprocessor family, which provides input to the subsequent financial correlation computation family. And other families, of course, can be used instead here, but they must match the required input and output. The data flow element connects the individual elements and so links the entire pipeline. Let's validate now the configuration, in particular including the pipeline. Here we will modify the pipeline to demonstrate a failing validation. We start a validation. And it's good to see that no problems were detected. Let's modify the pipeline now. We just define another processing element by dragging it from the palette and placing it into the pipeline. You might have seen that the family that we are using now in the family or algorithm configuration part, actually it's a family that is not matching anywhere in this pipeline and shall cause the validation to fail. We connect now the pipeline elements to the data flows from the financial data source to the preprocessor family. By placing the unmatching processing element into the analysis flow, the pipeline now becomes invalid. We save the changes and execute the validation. And see that there is now a problem. The problem view provides more information which part is failing, and it's exactly the new family element that we placed into the pipeline. We can resolve this problem easily by deleting just the new processing element. As we have a valid configuration, we can now derive the pipeline implementation for Apache Storm from our configuration. We need an empty directory where the configuration tool will instantiate the current configuration into. We select this folder as part of triggering the instantiation, and the tool produces the required Storm artifacts. Finally, the process ends with executing a generated Maven build specification. Let's have a quick look into the code, in particular the generated Storm topology. It integrates the configured families, their algorithms, declares the required Storm elements and connects them. In particular, it allows us to change the processing path at runtime, here switching between software and hardware-based correlation computation. Due to alternative paths and already distributed algorithms, the topology becomes rather complex. The instantiation also created the deployable artifacts, here in terms of a jar file that contains all algorithms and their dependencies. The pipeline artifact can now be uploaded into the QualiMaster infrastructure and executed through Apache Storm and the specialized hardware. This is showcased in another video. Let us quickly summarize this video. We've seen how a domain-specific configuration frontend on top of a generic product line tool can be used to configure a big data infrastructure, including the data analysis pipelines to be executed. The configuration provides the frame for changing the data processing at runtime, in particular to select the most appropriate algorithms from the configured families to cope with the changing environment. The configuration is not just turned into software and executed, but it is validated based on model constraints. This allows us to flexibly adjust the validation if needed, for example to prevent pipelines with certain properties, such as cyclic pipelines. Finally, the configuration is turned into software artifacts, including functionality for changing the data processing at runtime. If you're interested and looking for more details, please consult the links on our webpage. You want to try it out? Please stay tuned. We will provide a trial version of the configuration tool in the next weeks.